Clarification has been something else suggested as the speculation of the old unlimited effect. Various evaluations, other than those made by a colossal number of experts, support this thought, giving validation about how the universe began. In any event, the momentum universe of science, with new movements, brings us novel appraisals and viewpoints. These assessments challenge our points of view, where certain bits of information, for example, those from Neil deGrasse Tyson, have transformed into a monstrous figure in this affecting universe of science. Now, something attracting is going on with the James Webb Space Telescope. It's key to see something that could make us question the speculation of the universe's beginning. The James Webb Space Telescope has found 750 new universes. These frameworks are not precisely what we anticipated, driving us to reevaluate what we believe we knew about them. This disclosure ought to help us with valuing how colossal frameworks ended up being, so it's not astonishing that it's stirring up how we might interpret the universe. Before, specialists said that the Big Bang speculation was an excellent explanation for how the universe began. According to the speculation, around 13.8 billion years ago, the universe appeared through a jumbling event like the crazy story of the universe's first experience with the world. However, the photographs from the James Webb Space Telescope have tested this thought. These photographs show universes that are more unobtrusive, smoother, and older, most definitely not equivalent to what the theory of how things came to be predicts. According to the theory, as the universe stretches out, objects should look more discernible the farther away they are. By and by, these grandiloquent plans make an effort not to keep that standard. The speculation additionally states that, at the universe's very beginning, all of the matter that makes up the universe was fit into a second superdense point called a singularity. This singularity was unimaginably hotter than anything we might genuinely measure or create. This idea of a singularity comes from many conditions in genuine science proposed by Albert Einstein's theory of general relativity. Within the singularity, all the matter in the universe was squashed into a small space with incredibly high density. It was an epic measure of mass and energy pressed into a minuscule space. In simpler terms, experts have ceaselessly said that the theory of how things came to be was the way the universe began. At any rate, these new pictures from the James Webb Space Telescope are making us question that thought. The universes it found don't fit with what the speculation expected, and the theory's explanation of the early universe might not be as strong as we once thought. In our diligent viewpoint on the universe, we see that all the energy in the universe began from an extremely hot and dense point called a singularity. This point resembles the beginning phase for all that we view in the universe today. After the singularity, the universe started to develop and expand over 13.7 billion years to become what it is today. The expansion began with something many refer to as the Great Expansion, where the universe expanded rapidly, much faster than the speed of light. Perhaps the very fabric of space itself was expanding, and everything in it was stretching out along with it. This immense expansion helped shape the universe by making things more uniform and creating a path for galaxies, stars, and other cosmic objects to form. As the universe continued to grow, it didn't expand as quickly as during the Great Expansion, but still continued to develop. We call this ongoing development cosmic inflation. Experts have seen proof of this expansion through observations like how light from distant galaxies changes in color, known as redshift. Now, let's look at those stunning pictures of new galaxies taken by the James Webb Space Telescope. To the larger public, these photos look dazzling, with various galaxies in a single frame. At any rate, for researchers, it's somewhat a shock that these photographs don't match what their hypotheses expected. These galaxies are fundamentally older than anticipated, which challenges our point of view on galaxy formation and development. According to the Big Bang theory, there are also considerably more mature galaxies than we expected. The theory of the universe's beginning made assumptions about the number of galaxies there ought to be and how they should be spread out. At any rate, the JWST pictures show a colossal number of galaxies, some more than anticipated. This makes experts question whether the theory's calculations are precise. A few experts are even beginning to reconsider aspects of the theory, considering how these discoveries seem to contradict their previous assumptions. Another astonishing feature of the newly observed galaxies is their smoothness, which conflicts with what the Big Bang theory proposed. According to the theory, galaxies should show irregularities and patterns in their structures due to how they formed and evolved. However, photographs from the JWST reveal galaxies that are remarkably smooth, lacking the expected complexity and roughness typical of early galaxy formation. During the development of the universe, everything that makes up our universe was compressed into a small space. As the universe expanded and cooled, particles like protons, neutrons, and electrons began interacting with light and energy around them. These interactions played a significant role in the formation of matter in the universe. In the first few minutes after the Big Bang, a process called nucleosynthesis occurred, forming lightweight elements like hydrogen and helium. These elements laid the foundation for the development of stars, galaxies, and more complex elements as cosmic history unfolded. This combination of fundamental building blocks was essential for the universe's development, progressing from an initial state of particles and energy to a state where matter started to form as expected. The Big Bang theory had predicted galaxies would be scattered and chaotic. However, the JWST images tell a different story. Rather than seeing chaotic, scattered galaxies, the photos reveal smooth, round, and even spiral shapes, similar to galaxies we find in the modern universe. This surprising revelation challenges the idea that disorder is a natural part of galaxy formation. If there are few or no turbulent events occurring in these galaxies, as suggested by the Big Bang theory, it becomes difficult to explain how such small galaxies could have grown into massive systems. Similarly, the optical appearance predicted by the expanding universe theory, where objects appear smaller with increasing distance due to expansion, does not seem to be present. Experts have observed a striking pattern where large structures tend to cluster in massive groups, forming complex networks across the universe. This large-scale structure aligns with the expectations made by the Big Bang theory. According to the theory, the universe began in an extremely hot and dense state, and then expanded and cooled over time. As the universe expanded, gravity played a significant role in shaping how matter was distributed, guiding galaxy formation. The gravitational effects expected by the Big Bang theory are consistent with what we see today, with gravity organizing matter into galaxy clusters and forming interconnected filamentary structures known as the cosmic web. The presence of these galaxy clusters and the cosmic web structure strongly supports the Big Bang theory. How galaxies are distributed across the universe aligns with the gravitational effects predicted by a dense, expanding state as suggested by the theory. These elements, including galaxy clustering, the cosmic web structure, and the spread of galaxy clusters, provide strong evidence that the universe grew from a highly dense state and has been expanding for billions of years. Now, let's return to the size of the structures observed by the JWST. These images contradict what we thought we knew about the Big Bang theory. According to the theory, small galaxies should form and expand through collisions and mergers with other galaxies. However, the galaxies observed by the JWST seem very different from this concept. If cosmic structures were colliding and merging as expected, we would see evidence of these events in the form of distorted or irregular galaxies. However, the photographs show something entirely different. The Big Bang theory is still a highly compelling hypothesis, not just an idea without supporting evidence. It is backed by significant scientific data, including observations of redshifted light and measurements from distant galaxies. Studies showing galaxies moving away from one another suggest the continuous expansion predicted by the theory. The distribution of light elements like hydrogen and helium observed throughout the universe also supports the Big Bang theory. Furthermore, the large-scale distribution of galaxies revealed through cosmic surveys matches the models expected by the theory of how the universe began. One of the key pieces of evidence for the Big Bang theory is the discovery of the cosmic microwave background, CMB. The CMB is faint radiation that fills the entire universe and represents the leftover glow of the Big Bang. This significant radiation, first detected in 1965, provides crucial support for the idea that the universe began in a hot, dense state and has been expanding ever since. The discovery of the cosmic microwave background CMB was a groundbreaking moment in cosmology. The CMB is a remnant of the universe's early stages, emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, allowing light to travel freely. This radiation appears as a faint, uniform glow across the sky, providing a snapshot of the early universe. Measurements of the CMB have revealed slight temperature fluctuations that correspond to areas of varying density in the early universe. These fluctuations were the seeds from which galaxies and larger cosmic structures eventually formed. The CMB's precise characteristics, such as its uniformity and slight variations, strongly support the Big Bang model. However, despite this compelling evidence, the James Webb Space Telescope's recent discoveries have raised new questions. The unexpectedly smooth, well-formed galaxies observed challenge long-held assumptions about how galaxies evolved after the Big Bang. According to the Standard Model, early galaxies should have been chaotic, clumpy, and irregular due to gravitational interactions and collisions. The JWST images, however, show galaxies that are surprisingly mature and well-organized, with spiral structures and smooth shapes. This level of development was not expected so soon after the Big Bang, suggesting that galaxy formation may have been faster or more efficient than current models predict. Another unexpected finding from the JWST is the sheer number of galaxies observed in its deep field images. These galaxies are more numerous than models based on the Big Bang theory anticipated. If galaxies form earlier and more efficiently than predicted, scientists may need to adjust their understanding of the timeline of cosmic evolution. The redshift data from these galaxies also presents a puzzle. Redshift occurs when light from distant objects is stretched to longer wavelengths due to the universe's expansion. According to the Big Bang theory, higher redshift corresponds to greater distance and earlier points in time. However, some of the galaxies detected by the JWST have redshifts indicating they formed only a few 100 million years after the Big Bang, but appear more developed than expected. This contradiction has prompted some scientists to consider modifications to the standard cosmological model. While the Big Bang theory remains the most robust explanation for the universe's origin, its details may require refinement based on the latest observational data. One possibility is that galaxy formation processes were influenced by factors not fully accounted for in current models, such as variations in dark matter distribution or earlier star formation bursts. Another possibility is that the universe's early conditions were different from what scientists have assumed. Despite these challenges, the Big Bang theory's core principles remain well supported. The universe's large-scale structure, the observed expansion of galaxies, the abundance of light elements, and the CMB all provide strong evidence for a universe that began in a hot, dense state and has been expanding for nearly 14 billion years. The discoveries made by the James Webb Space Telescope represent a turning point in cosmology. They remind scientists that even well-established theories must adapt to new data. As the JWST continues to observe the universe in unprecedented detail, it will undoubtedly uncover more surprises that reshape our understanding of cosmic history. The universe remains a dynamic and evolving mystery, with each discovery leading to new questions and deeper insights. Science thrives on such challenges, pushing the boundaries of what we know and inviting us to explore the cosmos with ever greater curiosity and wonder.